In the previous segment, what we did is we started with the governing equations, x momentum, continuity, and energy, and we went through a non-dimensionalizing process. Well, you can use those same equations and use them to come up with a solution for the temperature and velocity profile in the case of a vertically heated flat plate. And what results, you can come up with a solution that then enables you to get the Nusselt number. And so for laminar flow, so this would be for a vertically heated flat plate, constant temperature. But if you go through the analysis, what happens is you would use a similarity solution, and it results in a nonlinear ordinary differential equations, a series of them, two of them. And those equations would be solved using numerical methods. And with that, within the equations, what we have are related to the Grashof number, or the solutions would be. And note here, the Grashof number is expressed as a function of x. So remember our coordinate system that we have imposed for this vertically heated flat plate, x going in this direction. So we're looking at the Grashof number at some x location. And what we can do with these solutions, the solutions will be derived or obtained through the numerical methods and numerical integration. And then in order to relate that to the Nusselt number, you have to go through essentially a curve fitting procedure and fitting functional forms to the data. And so one expression for the Nusselt number that results through that process is the following expression. And again, there will be different relationships that exist depending upon what type of curve fitting is being used. So that would be an expression that would be obtained for the Nusselt number. Now, that gives us the local value of the Nusselt number, very much like what we saw for the flat plate when we had forced convection. And so what that is doing is that would be quantifying the local heat flux at some location x, and so that would be location x there. Now, quite often we're interested in obtaining the average convective heat transfer coefficient across a plate, h bar. And so in order to do that, what we would have to do is integrate the local heat transfer coefficient. And so looking functionally, I won't go through it, but if you recall, the Nusselt number is hx over k. And with the relationship that we just have put here, we see that we have Grashof number to the 1/4. Well, Grashof number is x cubed, so that is x to the 3/4 is the Nusselt number relationship. And so with that, we can say that the Nusselt number relationship is x to the 3/4. And then notice that we have the x here. So if I want to isolate for h, that means that h is going to then be a function of, that will be 1, well actually it'll be k, but k is a constant, so we don't have to worry too much about it, but it would be over x to the 1/4 or x to the minus 1/4. And so with that, if we want to obtain, and so in here we're looking at h of x, and if we want to obtain the average convective heat transfer coefficient across the plate, we would integrate it over whatever the length of the plate would be, and we would do h of x dx, just like we did earlier for the flat plate. And with this minus 1/4, when we integrate that, what we end up with is a relationship that looks in the following manner. So it would be 4/3 of the value of h at the end of the plate. So if this is y and this is x, so let's say this is our plate here, x equals L, we would evaluate h at x equals L, and then h bar, or the average value for the entire plate, is then just 4/3 h at x equals L, which would be the convective heat transfer coefficient at the end of the plate. So that is what we get, and this is in the case of an isothermal plate that we were looking at. Where we said that this was T wall and T infinity was out here, and we said T wall was greater than T infinity. So that is the solution that we can obtain, and we had the functional form for the Nusselt number. There are different ones that exist in different books depending upon how the curve fit has been performed. But the main thing to remember, 4/3 h x equals L, and this is for laminar. It's not for the case of a turbulent flow, so we have not gone through the transition process yet.